Good morning. Welcome to the new lecture on sustainable manufacturing. Today we are going to finish the content on statistical concepts that we started in the previous class, which are necessary to do the analysis of the simulation data. So we'll continue on where we stopped the last time. We have covered the concepts of sample space, experiments, then we also talked about random variables. We also talked about what's a probability density function, distribution functions, PDF and CDF, cumulative density functions or distribution functions. We also talked about how do we look into what is the concept of independence, disjoint, all those kind of stuff. So today we are going to talk about how do we deal with simulation output and stochastic process. So the simulation output and the stochastic process is two concepts that is important for us to understand. So when people say stochastic process, we said about stochastic is something like equivalent to random. So if I say stochastic, assume that it's random. Random means you don't really know when the next event is going to happen. There is a variability associated with it. Not variability, uncertainty I mean. Okay. Let's say uncertainty as the word. Okay. So a stochastic process for us, okay, a process that has randomness in it, is a collection of similar random variables. So the random variables are similar, ordered over time. So these random variables are collected over time, or we say as data of random variables are collected over time, and these random variables, these RVs, are similar. Similar means they all part of the same process. That's what we are talking about. Okay, well defined over a common sample space. So that means this is all part of the same process or experiment. So we are basically saying that these random variables are ordered over time. The values of the random variables are ordered over time, and they are defined over a common sample space. Okay. Now the next most important thing is that common assumption. Okay, the common assumption in this regard. The common assumption we use is that we assume that a discrete event stochastic process be covariance stationary, which means the covariance does not change over time. That's the idea. Okay. As time progresses, the covariance of the process remains stationary. So if you graph it, you will kind of, if this is the time axis, it will kind of be stationary. It won't change over time. That's the thought process. Or another way is the mean and variance of the process, mean x bar or mu, whatever, and the variance sigma square or s square, either one of them is stationary over time. I hope that you guys have already read the textbooks on statistics and are familiar with the concept of mean, variance, standard deviation, median, mode, all those kind of stuff. Okay, so which means they don't change over time, the values remain same. But in a simulation, when you do a simulation analysis, discrete stochastic simulation analysis, if x1, x2, x3 is a stochastic simulation process, so these are the values of a random variable that is coming from a simulation process, and the simulation is beginning at time t equal to 0. Okay, it is quite likely, or most of the time it is true. Okay, most of the time it is true. What is true? That it will not be covariance stationary, or the mean and variance will not be stationary over time. Okay, the idea is that they will not be stationary over time, or the covariance of the process will change over time. Okay. So why is it important to us? Why is this covariance stationary is an important thing to us? because when you want to do analysis of the simulation data, this covariance stationarity is of importance for us to identify something. What do we want to identify? There is a concept called warm up period. Every system, it will take a little bit time to warm up. Okay. In many other times, in some simulations or in many of the simulations specifically related to manufacturing systems. Let's talk about manufacturing here a little bit. Specific to manufacturing systems. So assume that you come to a factory at 10 in the morning, you switch on the lights, you switch on the machine, you start loading the machines. So for some time, maybe 10 or 10:30, 11 in the morning, it will take some time for the entire factory to come to full flow. So that type of a period, is called as a warm up period. So in many of the situations in manufacturing, if you are doing the simulation, the xk plus 1, xk plus 2, or which means after a large value of k, if k is large enough, after a large value of k, you will see that these values of the random variables will start to behave like approximately covariance stationary process, or you will start to see after large k, we start to see the mean and variance, okay, or standard deviation, whatever you want to call it, becoming constant over time. So what we are saying here is that when the value of k is large, the initial warm up period is eliminated, then you start to see a covariance stationary process. Okay, and the length, this k, whatever it is denoted as the length of the warm up period. So if you look at the output of a system, it will look like this. This is your time and this is some output. You will actually start seeing it from 0. You will see all these kind of variations. It will go like this, and then after some point of time you will start seeing doing this. So you can basically say that up to this point is when the system was warming up, and here this is the value of k. Okay, this is the value of time period. Okay, at that time t equal to k is when the system transitions from a warm up system to a, so this behavior is what we call as steady state. Okay, and this is the process in which your covariance is almost stationary. So this is approximately covariance stationary. Okay, or you can think about that the mean and the variance are kind of steady over time. The most important thing that I want all of you to remember is the typical experience from all the people who work in the simulation field is that the simulation output data is almost always correlated. Okay, so simulation data is mostly correlated. Okay, almost always correlated. That is the best way for you to think about it. Okay, hence, what is the problem with the correlation or correlated data? The classic statistical formulas do not apply to analysis of those data. Okay, so here we can assume that since it is correlated, the independence assumption fails. Require new methods or different methods, different stats method. Okay, so we will see how we analyze simulation data in input and output analysis. We will talk about that later down the road. That is somewhere later down after we talk about the optimization and other stuff. But please remember this point is important for you to remember later for the entire duration of this course. Then we also talk about something called the law of large numbers. Okay, the law of large numbers is a scenario where the concept is quite simple. If you have a very large enough sample, okay, then your sample mean tends to be behaving very close to the real value of the real mean or expected value of the system. So the idea is this: if one performs an infinite number of experiments, okay, so if you remember we talked yesterday, here the experiment is, let's say, tossing a coin. I apologize. So your output is, your sample space is, you can get a head or a tail. Okay. So if you do the experiment 5 times, let's say, and you got the output as head, 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 head and tail, and if you try to estimate what is the percentage of head, then it will be 4 out of 5 is what you will get as the probability, which is not the real probability. But if you do this 5 times, this is what it is. If you do this 1000 times, you might get somewhere close to, let's say you get a value of 490 out of 1000 or something like this. If you do this 10,000 times, then you would get somewhere close to maybe 5070 by 10,000, something like this. Okay. So as you can see, this value will slowly approach towards the theoretical probability of 0.5. That is the idea here. Okay. Most of the time the probability will pretty soon it will converge to the theoretical value. Okay. So the idea is that if you do the experiment infinitely large number of times, if you do it large amount of time, then each experiment, each time when you do this large number, you get a sample mean, u bar or x bar, whatever you want to call it, and n is sufficiently large, it is big, okay, we are talking about thousands, 10,000s, those kind of numbers, then this u bar n or the x bar, whatever you want to call it, will be arbitrarily close to mu for almost all experiments. Or here you are saying that the sample mean will approach the true or population mean, okay, which means x bar will tend to become mu, or mu is your population mean. What does this law of large number implies to people who are doing simulation analysis? So for us, when we have to do it in practice, when we have to analyze the simulation data in practice, what we do is we run the simulation for a sufficiently large period of time. So we first simulate the system. So simulate the system for a long period of time to before finding x bar. Okay. So you run the simulation for a large period of time to get the estimate, or estimate is the maybe the sample mean or the average. So your large number, the n is sufficiently large. Okay. Then you repeat this many times. So if you do this, your first run, so run 1 you have an x1 bar, run 2 you have an x2 bar, run 3 you have an x3 bar, run 4 you have an x4 bar, like this. Okay, you will continue. So you replicate these runs many times. Okay, then you have until nth run you have an xn bar. Then you can use all these x bars to calculate the mean of means. So you can calculate x bar bar, which will be equal to x1 bar plus x2 bar plus x3 bar plus all the way until xn bar, okay, divided by n. So you take the mean of these means. Each mean you get from a replication. From there you do the means, and this mean of means will be very close to mu. or this is almost the true estimate of the population mean. That is what we talk about the, this is how the law of large numbers is put it into practice. Okay. So, law of large numbers implemented into the system is that you run, the first step is you run the simulation for a large number of sufficiently large period of time, so that the n is sufficiently large. Okay. This concept, n becomes sufficiently large. Then using that you find the estimate, you get your x1 bar, x2 bar, x3 bar. Okay. To do that you replicate, you keep the n sufficiently large. Here you are keeping n large. Okay. You keep n large and replicate the whole experiment, and then use these averages to calculate the mean of means. So, use this to calculate x bar bar or the mean, then use that mean to do the estimates. Alright. So, one of the things that we talked about is the importance of the concept of independence, disjoint, and all those kind of things. So, if you are given a bunch of data, how do you know whether the data is independent or not? Is there any way to identify that? Okay. So, we will actually go through a very simple example today in the class to show you how to test for independence. Okay. So, there are many ways, there are multiple ways you can test whether a sample data is independent or not. Okay. There are many statistical tests available, okay, to check for independence. All right. So, you check for the independence of the data using many tests, many statistical tests are available. One example test that we are going to cover, this is called as the chi-square test for independence, or we also call it as Pearson's goodness of fit test. Okay. So, this test will actually help you to decide whether the data is, whether we can use chi-square, this chi-square test for doing the test of independence. I would request you guys to read upon what is a chi-square. Okay, this kind of looks like this. Chi is a Greek variable, chi-square distribution. Okay, if you read about distribution of variance, then you will get to see the chi-square distribution. That's one part. Then shape of distribution, PDF and CDF, probability density, cumulative density function of the same. So, please read these kind of things so that you can understand what do I mean by chi-square distribution. Okay. So, but anyway, so the mechanics of the test we will go through, and you will understand the concept. Once you read it, you can augment the concept that way. So, the example problem that we are going to analyze is that the voting preference, is it influenced by gender? Okay. So, we are trying to see the gender, whether gender, okay, or sex of a person and voting preference, are they independent? This is the question what we are trying to follow. Okay. So, here we begin with the assumption that our initial thought process is that we assume, okay, same way as in the court of law, everybody is assumed to be innocent. Here we assume that gender and voting preference are independent, and we are going to check this assumption. If we do not get evidence to verify this assumption, then we can reject this assumption and say that okay, they are interrelated, or they are not independent, they are related. Same way as a person is assumed innocent, and based on the evidences that is provided in front of the court, the person is, if the guilty is proven beyond reasonable doubt, then the notion of innocence is rejected and the person is pronounced guilty. Same way, same process. This process is typically what is called as hypothesis testing. Okay. It is available again in the statistics textbooks. I know many of you have gone through these topics, but I request you guys to read this. Okay. Hypothesis testing of single mean, comparing two means, all these things please do read. So and there is also things about proportions. Okay. Please do read these concepts from the statistical books or revise your knowledge of statistics so that you can follow what here it is. So what we have here is that we have two gender, a male and a female, and there is three parties. This is the United States data, so the Republican, Democrat and Independent. Okay. So these are the stuff, and we have collected some sample. About 1,000 people were checked with this, and from the male, that there are 400 male and 600 female. Of the 400 male, 200 voted Republican, 150 voted Democrat and 50 voted Independent. Of the 600 female, 250 voted Republican, 300 voted Democrat and 50 voted Independent, kind of a thing. And so we are trying to find out whether the gender has an influence on the voting preference. So the first thing that we need to learn as a part of here is this concept is called degrees of freedom. Okay. So degrees of freedom is again a concept that is discussed very well in the statistical textbooks. Here the degrees of freedom is calculated as row minus 1 times column minus 1. So we have two rows. Okay. We are only looking at this is the data that we are looking at. Okay. So we have two rows, three columns. Okay. This is not used. So we have three columns. So this is R1 and R2. This is C1, C2 and C3, three columns. Okay. So it is, since there are two rows, that's 2 minus 1. There are three columns, that is 3 minus 1. So that is 2 minus 1 is 1, 3 minus 1 is 2. So it's 1 times 2, 2. So the degrees of freedom is 2. Lot of people have this question about what is the degrees of freedom. Textbooks explain this very well. One simplest way to look at it is that it is the number of now if you think about it as a data set, okay, it is how many of those data sets, data points among the data set can be independently determined. Like for example, if you have 4 data values, okay, it's given to you. Let's say 4 data values. Okay, let's say 6, 12, 9, 10, something like this. And if you use these 4 values to find an x bar, okay, which is a sample mean. So if I give you the x bar and I give you 3 of these values, any of the 3 values, then you can find the 4th value, because you know that x bar is equal to x1 plus x2 plus x3 plus x4 divided by 4 in this case. So any 3 plus the x bar gives you the you can use it to find the 4th value, or any of the 3 is what is required along with the x bar. So degrees of freedom is that typically it is usually 1 less than the in many other people they call it as n minus 1 and those kind of things. Not necessarily true, this is calculated in many different ways, but please do read the concept of degrees of freedom from the statistics books that we are recommended earlier. Once you calculate the degrees of freedom, the next thing what you need to do is you need to calculate the expected values. Okay, the expected value of each one of the row column, ERC, is the expected value calculated, which is calculated from the for column 1, column 2, column 3. Then so this is R1 column 1, R1 column 2, R1 column 3. There is R2 column 1, R2 column 2 and R2 column 3. Okay. So for each one of the ones, so from 1 1 column 1, R1 column 1 to R2 column 3, 1 1 to 2 3. Okay. For each column you are supposed to calculate the expected value. How are you calculating the expected value? Number in the row multiplied by NR is the number in the row multiplied by NC, number in the column, divided by N. N is the total value. So here n, little n is equal to 1000, and the NR can have values which is 400 and 600. NC has the values, number of columns has the value 450, 450 and 100. Okay, you kind of know what I am talking about. These are the NC values, these are the NR values, and here is your N. Okay, you use that to find it, and from there you find the chi-square value. This is the chi-square. Okay, this is actually written like this. Chi is kind of a chi-square. Okay, so the chi-square value is sigma or summation. This is a summation sign. Okay, the summation of difference between O is, this is the observed value. The observed value is this. These are the observed values. Okay, minus the expected value, ERC, you are already calculated it, and then you divide by the expected value, and then you sum those ratios and you will be able to get the answer. So let us do one thing, let us actually solve this problem. So we will try to do that. So the setup in such a way for us was that it is male, we had female. Okay, we had male data was for Republican, Democrat and independent, and we had a total here. Okay, so the Republican data was 200, Democrat data for male was 150 and independent was 50, and a raw total of 400. And for female, the Republican was 250, the Democrat was 300 and independent was 50 with a raw total of 600. The column totals were 450, 450 and 100, and the total sample in both cases was a 1000. So if you calculate the expected values, okay, so the if you do that, so the expected value of 1 will be equal to, remember that it is NR times NC divided by N. We use that, the NR for the first row will be 400. Okay, this is the first row. Then NC column for this one will be 450. Okay, divided by 1000. Okay, which will give you the value of approximately 180. Okay, this will be the value of E11. If we do E12, which is the second one, expected value of this, that would be equal to 400 times this is the 400, then the second 450 divided by 1000. That will give you again the value of 180. Okay, that 180 is for this particular case. Then the third one is E13, which is equal to again 400 as the raw value, column value is 100 divided by 1000, and you get a value of 40 in this case. Okay, so that value gets goes into this one. So if you follow that process, the E21 will be pretty much will be 600, that's the next row, times 450, that is the column, this column, divided by 1000. Okay, that will give you a value of 270. E22, the second case, it will be 600 multiplied by 450 by 1000, and that gives you again 270. And E23, expected value of 23, here it will be equal to row multiplied by column divided by 1000 equal to 60. That value is again as this. So if you write that matrix, the expected value matrix, it will look like this: male, female, and you will have 180, 180, 40, 270, 270 and 60. So these are the expected values that gets compared 1-to-1 correspondence. Then by the previous equation, if you look at it, you calculated all the expected values now. Now you have to calculate the chi-square. Okay. So the chi-square equation, we know that chi-square is calculated by sigma summation of observed value of raw column minus expected value of raw column, okay, the square of that divided by the expected value of the raw column. Okay. If we want to do this, then the chi-square can be calculated in this regard equal to, we will take the first one, this is your R1 C1, or we can call this as 1 1, this is 1 2, this is 1 3, this is 2 1, 2 2 and 2 3. That's the case. Then we have, it is the first case, it will be the observed value is for the first 1 1 will be 200, okay, and then from that the expected value for that, it is 180, square of that divided by 180, that will be the first one. Then for 1 2, it will be observed value is 150, the expected value is 180, square of that divided by it will be divided by 180, because that's the expected value, ERC, this is the ERC. Okay. So this is your 1 1, 1 2, 1 3, 2 1, 2 2 and 2 3. Okay. All right. Plus the next one comes is your summation, you are summing the whole thing up. The observed value for the 1 3 will be 50, expected value is 40, square by 40, plus now if you do the third, the 2 1. Okay. So this is for 1 1, 1 2, 1 3. Now we are doing is a 2 1, which will be observed value is 250, expected value is 270, square of that divided by 270, this will be 2 1, plus the 2 2 will be the observed value is 300, the expected value is 270, square of that divided by 270, and that will be 2 2, and the last one plus will be the observed value is 50, the expected value is 60, the square of that divided by expected value, which is 60. This is your 2 3. Okay. All those values are summed up. So you will get the values equal to this will come to 400 by 180, plus this next one will come to 900 by 180, the third one will come to 100 by 40, then fourth one will come to 400 by 270, plus the next one will come to is 900 by 270, then the third one will come to is 100 by 60, okay, which will be equal to, if you do the math, it will come to 2.22. I am only doing the 2 decimal places, plus 5 plus 2.5 plus 1.48 plus 3.33 plus 1.67. Okay. All of these values are equal to 16.2. Okay. This is the chi-square value that we get. So 16.2 is the chi-square value of the given sample. Now, how do we make a decision based on this value? So there is a table that is available in the statistics books. It is called the chi-square reference table, which contains the critical values. Okay. So the critical values of chi-square table is and you check that critical values using degrees of freedom. So the degrees of freedom we calculated earlier here, the df was calculated equal to 2, and if you find that I want to prove, you have to also say what is your confidence level, or the level above which you are confident. Okay. So that part. So here we are going to take the level of confidence equal to 95%. I am saying that okay, I want to be 95% sure. So if you take these values and you get this, then the critical chi-square value from the table, chi-square critical, this is our chi-square sample that we calculated from the sample data. critical will come approximately close to 6. So now we compare these values. Since chi-square sample is greater than chi-square critical, we are quite confident. We are quite confident that our initial assumption that the gender does not influence the voting preference is not correct, and we reject the notion that the gender and voting preferences are independent, and we assume that gender do influence the voting preference. So they are not independent anymore. Okay. I assume that by this you guys are able to understand how we are able to study the how we can work out the concept of independence through a simple set of data. And I would really, with this we conclude this lecture today, but I really request you guys to study this concept all by yourself a little bit more, so that we can, in the later part of the courses when we are talking about optimization and other parts, you will all be able to pick it up better. Thank you for your time.